Welcome back to the Power Quality Lecture Series. In this video, we are going to discuss about various harmonic sources. As you all know that modern industrial facilities are characterized by widespread applications of nonlinear type of loads. And these loads can make up a significant portion of the total facility loads, and it injects harmonic current into the power system, and which causes the harmonic distortion in the voltage. So this nonlinear type of loads having relatively low power factor. So industrial facilities often utilize the capacitor bank to improve the power factor to avoid the penalty charges, etc. So the applications of power factor correction capacitor can itself potentially magnify the harmonic current from the nonlinear loads. That may leads to the resonant conditions, etc. So there are a lot of adverse effect even when we are connecting a capacitor in order to improve the power factor. So nonlinear industrial loads can generally be grouped into three categories like switching devices, then arcing devices, and saturable devices. So in the switching devices, we are going to discuss some harmonic effect of three-phase power converters. So three-phase power converters can be either a voltage source inverter, current source inverter, or a three-phase rectifier, etc. So three-phase power electronics converters, it is having a difference from a single-phase converter because single-phase converters mainly generating third harmonic current, but a three-phase converters do not generate third harmonic currents. So this is a great advantage because third harmonic current is the largest component of harmonics. So however, they can still be significant source of harmonics at their characteristics frequencies, and we can see the harmonic spectra and source current waveform pattern for a current source inverter type adjustable speed drive here. You can see how much the current waveform is distorted, and the harmonic spectrum also. So here also you can see current and harmonic spectrum for a PWM type adjustable speed drive. You can see that voltage source inverter drives have much higher distortion level. In this waveform, you can see the current pattern is much more distorted in this case in a PWM type adjustable speed drive than the earlier figure. So, and this one actually a three-phase rectifier is another type of a nonlinear load, three-phase rectifier with a resistive load. You can see the voltage and current. This is a plot of a source voltage and current. When you are connecting a three-phase source to a three-phase rectifier, AC source to a rectifier, when you are plotting a source voltage of a particular phase and its current, you can see that the blue waveform is the source voltage, and current waveform you can see that it is distorted, and it is almost like a square wave pattern. When you are plotting a total harmonic distortion for this particular current waveform, when you are connecting a three-phase rectifier with a resistive load, it is around 28.13%. It is not at all recommendable because in IEEE standard, as per IEEE 519 standard, we should keep our THD of the source current should be below 5%. So you can see it is around 28.13%, and you can calculate what is the effect of this THD in your power factor, input power factor. You know that input power factor is equal to is a product of displacement factor and distortion factor, and displacement factor is nothing but it is cos phi, And distortion factor is the terminology that accommodate the effect of harmonic distortion, and you can calculate for this particular waveform. If THD is 28.13%, you can calculate the distortion factor as per the equation given. You can see that the equation is the value is 0.963. So if your power factor, suppose if you are maintaining the power factor as 1, because of this harmonics, now the power factor become 1 into 0.969. 0.963 is the power factor. That is the effect of harmonics in your system. This is another simulating diagram for a single phase controlled rectifier. You can find out using MATLAB. You can find out what are the harmonic effect by plotting source current and total harmonic distortion. And this is the simulation output of that particular converter. This is a rectifier, and it is plotted source current, output voltage, and input voltage here. So in this you can see type of nonlinear load and typical waveform and corresponding THD. A single phase uncontrolled bridge rectifier, it is THD is around 80%, because the third harmonic component is predominant there. So THD value is around 80%, very large. A single phase semi controlled bridge rectifier, second, third, fourth harmonic components are present. And in a 6 pulse rectifier, a 6 pulse rectifier is nothing but is a 3 phase rectifier. If you are using output voltage filtering, THD is around 80%. Without any input filter, you will get a THD around 80%, and 5th, 7th, 11th harmonics are present in that system. And this one, a 6 pulse rectifier with the output voltage filtering, and there if presence of a 3% reactor filter at the input side, the THD is around 40%, and 5th, 7th, and 11th harmonics are present. You can see the nature of current waveform. Then 6 pulse rectifier with a large output inductor, the again THD is reduced to 28%. And if you are increasing the number of pulses, definitely the THD will decrease. The harmonic distortion will be increased if you are increasing the number of pulses. If you are using 24 pulse or 48 pulse converter, the harmonic component can be reduced. THD can be reduced. So if we are using a 12 pulse rectifier, the predominant components are 11, 13, etc., and lower order harmonics are absent there, and around 15% is the THD. So that is the thing about the rectifiers. And another type of switching devices are DC drives or AC drives. Drives, you know that rectification, in case of a DC drive, rectification is the only step required for DC drive. So when you are from the AC supply, you need to convert into DC, and that DC is given to the motors. So that is a basic structure of a DC drive, and that controllable rectifier is a nonlinear device, and that will generate the harmonics. So in case of a DC drive, only the conversion is AC to DC. So therefore, they have the advantages of relatively simple control systems compared with the AC drive system. The DC drive offers a wide speed range and higher starting torque. And this particular DC drive, it is shown here, is a 6 pulse adjustable speed drive. We are a 3-phase rectifier, controlled rectifier used, and the largest harmonic current components are the 5th and 7th harmonic components are present in this case of rectifier. And the most of the DC drives are using 6 pulse rectifier, Large drives may employ 12 pulse rectifier. As you all know that if you are increasing the number of pulses, you can reduce the harmonic content also, and but this that reduce the harmonics, but that is much costly if you are using a 12 pulse or 24 pulse converter. And this particular 6 pulse converter, the largest harmonics currents are 5th and 7th. And in case of a 12 pulse rectifier, we are expected to eliminate about 90% of 5th and 7th harmonics, depending upon the system imbalances. But the disadvantages of 12 pulse drive are that there are more cost in electronics and another transformers also required in a 12 pulse rectifier. So it is costly. Even though the THD can be reduced, a 12 pulse rectifier is costlier when you are thinking about a DC drive. Then AC drive. So in AC drives, the rectifier output is inverted to produce a variable frequency AC voltage for the motor. So there are two-stage conversion here. The inverters, as you all know, it can be classified as a voltage source inverter or a current source inverter. And VSI actually requires a constant DC voltage input to the inverter. And this is achieved through some capacitor or LC filter, etc. in the DC link. And the CSI, current source converter, requires a constant current input. So where we are using a series inductor placed in the DC link. And these AC drives actually generally use standard squirrel cage induction motors. This particular arrangement here I have shown is a PWM adjustable speed drive. You can see the voltage waveform. So these also generating the harmonic. You can see the voltage pattern here. Large ASD. The first one is the voltage source inverter fed induction motor or AC motor drive, and second one is the current source inverter fed motor drive. In both cases you can see the voltage waveform pattern. So these are main sources of harmonics in our system. Here you can see that effect of operating conditions, effect of PWM adjustable speed drive speed on the current harmonics. Depending upon the speed also, the harmonics injection into the system will be different. So there is a sufficient, there is a definite impact of operating condition. The harmonic current distortion in adjustable speed drives is not at all constant. Actually, the waveform changes significantly for different speed and torque values. Actually, the drives are using for that motion control. We are continuously changing the speed and torque, and depending upon that, the changes in the speed and torque also, the harmonic current also will be changing. Here I have shown a figure with the two operating conditions for a PWM adjustable speed drive. While the waveform at 42% speed is much more distorted, proportionately, the drive injects considerably higher magnitude of harmonic current at rated speed. Here it is shown as rated speed and 42% speed. You can see the bar chart, which shows that the amount of current injected is shown here. So you can see that at the 42% speed, you can see the waveform pattern which is more distorted, and hence it injecting more harmonic in the system. So these drives are depending upon the operating conditions, whether how much speed or torque is providing. Depending upon that, harmonic or waveform shape also will change. Then arcing devices. Actually, this category includes the arc furnaces or arc welders, discharge type lighting like fluorescent, sodium vapor or mercury vapor with a magnetic ballast. And you can see in the figure an arc is basically a voltage clamp in series with the reactance that limits the current to a reasonable value. And the voltage current characteristics of a arc are nonlinear. And this electric arc is the major source of voltage harmonic in the system. And during arc, current exceed will be excess of 60,000 amps are common. And an electric arc itself we can represent it as a source of voltage. That is a source of voltage harmonics. It can be represented as a source of voltage harmonic. And if you are measuring, or if a probe were to be placed directly across the arc, one would observe a somewhat trapezoidal waveform, and its magnitude is a function of a length of arc. So this kind of arcing devices injecting a lot of voltage harmonics into the system. Then saturable devices. So equipment in this category includes the transformers and other electromagnetic devices with a steel core, including motors. So harmonics are generated due to the nonlinear magnetizing characteristics of steel. You can see the transformers operated in a saturated region purposefully. The power transformers are designed to normally operate just below the knee point. Below the knee point, you can see a magnet current VI characteristics here. Below the knee point, it is almost linear. After that, in that magnetic saturation characteristics, above the knee point, the VI chara is non-linear as shown in figure. So the power transformers normally designed to operate at below the knee point. The operating flux density of transformer is selected based on the optimization of steel cost or no load losses or noise, etc. Many electric utilities will penalize transformer vendors by various amounts for no load and load losses. And a high cost penalty on the no load losses or noise will be generally result in more steel in the core and higher saturation curve that yield lower harmonic current. So you can see that transformer magnetizing current and its corresponding harmonic spectrum is shown here. A typical characteristics. And here we can, these are the some of the sources that is typically from industrial side, switching devices, arcing devices, and saturable devices. And then we can discuss something about what is the effect of harmonics in the power system devices. What are the effect of harmonics on power system devices? So here you can see that some of the typical characteristics or typical characteristics of current waveform. That is, first one is a nonlinear current drawn by a single personal computer. You can see how much it is distorted. That is what is this particular waveform. We are expected to be in a sinusoidal, and now we can see the waveform pattern. It is not at all in a sinusoidal shape. It is completely distorted. And you can see second one is a nonlinear current drawn by a single computer video monitor. So this is what is the effect of harmonics in the system. And you can see that what makes harmonics so dangerous, that is very often the effect of harmonics are not known until some failures occurs. So only after some failure occur we will notice the effect of harmonics. And insight into the how harmonics can interact within the power system and how they can affect the power system component is important for preventing the failures. So let us discuss about what is the effect of harmonics in your transformers. So harmonics can affect the transformers primarily in two ways. The voltage harmonics produce additional losses in the transformer core, as the higher frequency harmonic voltages set up the hysteresis loops, which superimpose on the fundamental loop, and it will increase the losses. A second and more serious effect of harmonics is due to the harmonic frequency current in the transformer windings. And this harmonic current increases the net RMS current flowing in the transformer windings, which results in an additional I square R loss. That is another effect. And winding eddy current losses are also increased. Winding eddy current are circulating current induced in the conductor by the leakage magnetic flux. And this harmonic loads can handled by a factor which is known as K factor rating. One method by which a transformer may be rated for suitability to handle harmonic loads is the K factor ratings. So actually the K factor rating is equal to the sum of the square of the harmonic frequency currents, which is expressed as a ratio of total RMS current multiplied by the square of the harmonic frequency numbers. Here you can see the K factor rating K is equal to I1 square, that is representing the fundamental. So it is 1 square plus I2 square, second harmonic. So 2 square plus I3 square into 3 square, etc. In square into n square. N is an order of harmonics. But where I1 is actually the ratio between the fundamental current to the total RMS current. And I2 is the ratio between second harmonic current to the total RMS current. I3 is the ratio between third harmonic current and total harmonic current, etc. So you can more generally you can write it as a K equal to sigma In square H square into the In square H square, where H is equal to 1, 2, 3, etc. N. So for example, this actually representing how much your transformer can withstand with the harmonics. So suppose determine for an example I have given one problem. Determine the K rating of a transformer required to carry the load consists of 500 amps of fundamental current, 200 amps third harmonic current, 120 amps of fifth harmonic current, and 90 amps of seventh harmonic current. So if you have a load with this pattern, which having 500 amps of first fundamental current, 200 amps third harmonic, 120 amps fifth harmonic, and 90 amps of seventh harmonic. And then you need to find out the K rating of the transformer required. So as per our equation, total RMS current you can calculate. RMS is the root mean square. So square root of 500 square plus 200 square plus 120 square plus 90 square is equal to 559 amps. And in order to find out the K rating, you need to find out what is I1, I3, I5, I6, etc. Here it is I1 is present, I3 is present, I5 is present, and I7. So I1 is a fundamental current 500 divided by total RMS, that is 559. We will get 0.894. And similarly, here I3 is 0.358 and I5, I7 are calculated. So I3 means 200 amps divided by 559. I5 is 120 by 559, etc. So you can calculate from that equation, you can calculate K is equal to I1 square, 1 square, and then I2 square, 3 square, etc. You will get K factor as 4.378. So K factor is now 4.378. So what does it mean? The transformer specified should be capable of handling 559 amps of total RMS current with a K factor of not less than 4.378. So the K factor of the particular transformer should be equal or greater than 4.378. Then only that particular transformer can handle that particular load with the harmonics given. Typically, transformers are marked with a K rating of 4, 9, 13, 20, 30, 40, and 50. So a transformer with a K rating of here in this particular problem you need to choose something that is greater than 4.378. So standard value is 9. So a K rating of 9 should be chosen here. And if you are chosen a transformer with a K rating of 9, such kind of transformer would have the capability to carry the full RMS load current and handle winding eddy current losses equal to the K times the normal rated eddy current. So in general, you can see that it can handle all the harmonics present in the load if you are chosen the transformer with K rating 9. So that is what is the effect of harmonics in our transformer. Then see what is the effect of harmonics in the AC motors. The application of a distorted voltage to a motor results in additional losses. That is what is the important thing. This will result in the additional losses in the magnetic core of the motor. So hysteresis and eddy current losses in the core increases as higher frequency harmonics voltages are impressed on the motor voltage windings. Eddy current and hysteresis losses will increase. This hysteresis losses increases with the frequency, and eddy current losses, you know that it increases as the square of the frequency. So you can imagine how much increase in the loss will be there with the presence of harmonics. And also harmonic current produces additional I square R losses in the motor winding. That should also taken care. So and some other effects are a motor exhibit torsional oscillations due to harmonics. Torsional oscillations will be there in AC motor. And the predominant harmonics found in a typical power system are 5th and 7th harmonic. And this will adversely affect the operation of AC motors. Those things you might remember studied already harmonic effects in the AC motors. And it will largely affect the excessive vibration and noise in the motor operating in a harmonic environment. And what are the effect of harmonics in the capacitor banks? Capacitor banks are commonly actually found in the commercial and industrial power systems to correct the or improve the low power factor. And capacitor banks are designed to operate at a maximum voltage of 110% of their rated voltage and at 135% of their rated kVAR. So large levels of voltage and current harmonics will leads which will exceed the rating and failures may occur. So when large level of voltage and current harmonics are present in the system, there is a rating of a particular capacitor bank. Often it exceeds and resulting in the failures. That is because of the reactance of the capacitor bank is inversely proportional to the frequency. Reactance of the capacitor is inversely proportional to the frequency, and the harmonic current can find their way into the capacitor bank easily. So higher order harmonics means the reactance will be reduced. So capacitor bank act as a sink, absorbing stray harmonic current and causing overload and subsequent failure of the bank. That is what is the effect you can see in your capacitor bank. And there is an effect of a more serious conditions with the potential for substantial damage occurs due to the phenomenon called harmonic resonance in capacitor bank. Actually, the resonance conditions are created when the inductive and capacitive reactance become equal at one of the harmonic frequency. At any one harmonic frequency, capacitive and inductive reactance are equal, means the resonance condition occurs that will damage the capacitor bank. That is a more severe condition. There are two types of resonance, as you all know, that series and parallel resonance. And in general, series resonance produces voltage amplification and parallel resonance results in a current multiplications. So there is a possibility of harmonic resonance in capacitor bank with the presence of harmonics. Then what are the effect of harmonics in cables? You can see that current flowing in a cable produces I square R losses. And when the load current contains harmonic content, the additional losses are introduced. Actually, in order to explain this problem, the effective resistance of the cable increases with the frequency because of the phenomenon known as skin effect. Effective resistance and skin effect, you might remember that. Skin effect is due to unequal flux linkage across the cross section of the conductor, so which causes the AC current to flow only on the outer periphery of the conductor. This actually has an effect of increasing the resistance of the conductor for AC currents. So the higher the frequency of the current, the greater tendency of current to crowd at the outer periphery of the conductor, and the greater the effective resistance for that frequency. Okay, so that will increase the I square R losses. And this effect of harmonic in cables can be you can express by the rating can be expressed in terms of current rating factor, which is represented as Q. The current rating factor is the equivalent fundamental frequency current at which the cable should be rated for carrying nonlinear loads containing harmonic frequency component. This K factor rating we already discussed in transformer, where K factor rating is actually the rating required to handle the load with a particular harmonics. Here also, this is the current rating factor Q, which is equivalent to fundamental frequency current at which the cable should be rated. That will be the criteria for selecting the rating of the cable in order to handle the nonlinear loads containing harmonic components. So this you can represent it as Q, which is equal to I1 square E1 plus I2 square E2 plus I3 square E3 plus etc. In square En, where I1, I2, I3 are the ratios of harmonic frequency current to the fundamental current. And E1, E2, E3 are the skin effect ratios. And this E1, E2, E3 skin effect ratio, or you can see that E2 is resistance at second harmonic frequency divided by resistance at a fundamental frequency. That is E2. Skin effect ratio means E2 is corresponding to resistance at a second harmonic frequency to the resistance at a fundamental frequency. E3 means resistance at a third harmonic frequency divided by resistance at a fundamental frequency. So we can calculate the value of Q in order to find out the rating of the cable. Suppose the Q value is 1.135 by considering third harmonic and fifth harmonic, seventh harmonic current, and you calculated using equation. Q is 1.135 means that cable should be capable of handling 50 hertz equivalent current of 1.135 times rating. RMS value of the current. If RMS value is 250 amps means 1.135 times 250. Fundamental value is 250 means fundamental value of the current is 250 means if your Q factor or current rating factor Q is 1.135, then the cable should be capable of handling a current of 1.135 times 250, that is 284 amps. So you should, here you consider the handling capacity of the harmonic current also. So that is what is the importance of current rating factor. And the effect of harmonics in busways. So most commercial multi-story installations contain busways that actually serves as the primary source of electrical power to the various floors. And these busways that incorporate the sandwiched bus bars are susceptible to the nonlinear loading, especially if the neutral bus carries large levels of triplet harmonic current. This should be the harmonic effect should be taken consideration. Then under the worst possible condition, the neutral bus may forced to carry the current equal to 173% of the phase current. So these busways are mostly you can see in multi-story installations. Under the worst possible condition, the neutral bus may forced to carry current equal to 173% of the phase current. And in case where substantial neutral currents are expected in your system, the busways must be suitably derated. It should be designed accordingly. So there are some parameters like bus duct derating factor in order to choose the rating of busways. These are the effect of harmonics in various power system equipment. Here you can see here I have tabulated all these effects. Equipment is given and effects of harmonics also. So in a rotating machines, harmonic losses, harmonic torque, speed torque characteristics, cogging, etc. So you can see that in transformers, core loss, copper loss, there are effect on core vibration, saturation problems, etc. Then transmission system, measuring instruments, power system protection, capacitor bank, uh, uh, consumer equipments, the effect of harmonics in generator, motor, relaying, switchgear, communication circuit, etc. There you can refer the textbooks. You can refer the textbook Power Quality by C. Shankaran. All the details are taken from that textbook for this particular topic.